All right, great. So our next speaker's here and ready to go. So I would like to introduce Jianlin Liu. He's going to be presenting type-preserving, dependence-aware guide generation for sound, effective, amortized probabilistic inference.
Thank you, Chair. Hello, everyone. This is Jianlin. This paper is about sound effective amortized inference. This is a collaborative work with Leni, Pengyuan, and my advisor, Yizhou. So first, what are PPLs, probabilistic programming languages? PPLs are very powerful tools for modeling and solving Bayesian inference problems. And PPL has three essential features, namely sampling, observing, and inference. Sampling corresponds to making random choices, and observing amounts to conditioning on a value being sampled from a distribution. Combining sampling and conditioning means a probabilistic model program defines a conditional distribution. Bayes' theorem describes how a probability or probability density of an event based on prior knowledge should rationally update according to observations. And finally, inference corresponds to applying Bayesian inference to infer the conditional distribution, the true posterior of that given the observed data x. Here's a very simple PPL program. This program takes an observed value x as input. There are two random variables Z1 and Z2 of standard Gaussian. The observed statement takes a distribution and an observed value. The observed statement does conditioning. It conditions the model that the observed x is a sample from this normal distribution. And this normal distribution has a mean of Z1 plus Z2. We expect to get the posterior distribution if we apply Bayesian inference to this model program. However, it is infeasible to draw samples directly from the distribution. If we run the model program forward, we only draw samples from the prior distribution. The observed statement only multiplies the density by a likelihood term. It is a null statement in terms of drawing samples. What we really want is to draw samples from the true posterior. Important sampling is one of the most popular inference algorithms. It uses a proposal distribution Q to propose samples, and it uses this formula to adjust the probability density. For example, we can use the exact prior distribution as a proposal. However, it might not be a good proposal since it does not make use of X. A good proposal distribution, a guide program, should produce samples with a high chance of being sampled from the true posterior. To find a good proposal, we can parameterize Q with a set of variational parameters phi. This guide program makes the mean and the standard deviation of that dependent on the observed value x. It does so by using neural networks NNZ1 and NNZ2, which are universal function approximators. It takes observation x as input and output the parameters of these two Gaussians. And phi stands for the learnable parameters of these two neural networks. We want to find a Q phi close to the true posterior on average. This Q phi is the guide program parameterized by neural networks. A modern deep learning framework can be used to minimize this objective. The expected KL divergence from the true posterior to the proposal. Training is actually amortizing over the space of observations. And this inference algorithm generalized from important sampling is called deep amortized inference. There are two stages in it. The ahead of time training stage is to find such phi. Guide programs Q parameterized by phi and x can be applied to different observations repeatedly at runtime. Then, at runtime, with such Q phi, the learned guide program inference would hopefully be cheap. And this project aims to make deep amortized inference easy to use, ineffective. This text is challenging because it requires generating good guide programs, and we address this challenge by synthesizing guide programs that are not only faithful and parsimonious, but also satisfy a soundness condition called absolute continuity. I will explain these things in the following slides. Faithfulness matters. A faithful guide does not contain conditional independencies that are not found in its model. Here is the same model program from earlier slide, also the Bayesian network of it, and the scatter plot of the true posterior. This model condition set Z1 plus Z2 is close to X. So the larger Z1 is, the smaller Z2 likely is. In that sense, Z1 and Z2 are correlated. This is the same guide program we saw earlier. It treats all random variables independent. It fails to capture the correlations encoded by the model. And there is a knock-on effect on importance sampling. As this plot shows, importance sampling with trained guide 1 cannot adequately sample from the true posterior. By contrast, guide 2 faithfully captures correlations in the model. It does so by making Z2 depend on Z1. Guide 2 leads to high-quality approximation of the true posterior, as evidenced by the last two plots. We want guides not only to be faithful, but also parsimonious. Parsimonious guides do not include more conditional dependencies than necessary, and fewer dependencies means strong learning signals in the training stage. Here is an example generalized from the previous. Let's call this model upside-down tree. There are several ways to construct a faithful guide program. If we sample random variables in the same order as in the model program, while ensuring faithfulness, we end up with a dense guide. A guide that has many dependencies. But if we sample random variables in a different order, we can get a program with a sparse dependence structure, and it is still faithful. There's a third way of constructing guide programs from literature. Previous work ignores the dependent structure of the model and uses hidden state of a recurrent neural network to make all random variables correlate. It would be wasteful to expend resources on learning spurious correlations. Later we will see parsimonious guide can lead to better performance. Besides faithfulness and parsimony, there is a crucial soundness condition called absolute continuity. A guide with incompatible support causes inference to crash or produce incorrect results. For example, a guide program that uses a gamma distribution would be incompatible with a model that uses a normal distribution because it is impossible for this guide to propose samples that are negative reals. And both training and inference of deep amortized inference require AC, since these two formulas are well defined only when AC holds. The real challenge in guaranteeing AC is proposed by general recursion and stochastic branching. Here is a probabilistic context-free grammar written in parallel PPL. It defines a probabilistic context-free language of arithmetic expressions such as 2.7 plus 3.14. The first argument of sample is an address string that denotes the name of the sample site. The PCFG function samples a syntax tree. Half the time it samples a leaf node of the syntax tree. Other time it recursively generates two subtrees. In trace-based PPLs, a program defines a distribution on traces. This is a possible trace. It goes to the else branch since 0.7 is than 0.5. And for the two recursive function calls, it first samples a leaf node const 2.7, and the second one samples const 3.14. AC in trace semantics requires an enumerable set of traces on which the model has a positive probability. The guide should also have a positive probability on it. For example, this is an unsound guide on the right-hand side. It is unsound for two reasons. First, the gamma distribution has a smaller support than the normal distribution. Second, the condition of the if statement breaks AC. The model and guide programs enter different branches of this if statement for the same value of A. Thus, these two programs are defined on incompatible set of traces. On soundness aside, this guide program is unfaithful. Since it does not encode correlations, it treats all random variables as independent. In fact, it is not entirely clear how to even manually create a faithful yet parsimonious guide for this PCFG model because of general recursion. The goal of this project is to make deep amortized inference easy to use, sound, and effective. So we designed a guide synthesizer called Fidelio. Fidelio automatically generates guide programs that are faithful yet parsimonious and satisfy absolute continuity. For soundness, we design a behavioral trace type system. For faithfulness, we propose a dependence analysis based on program dependence graphs. Then, a type dependence aware translation finally generates the guide program. We formalize the semantics using a calculus. It has a pure deterministic fragment and a monadic probabilistic fragment. This is the previously shown PCFG model program, but in Fidelio syntax. Variables in the monadic fragment are shown in bold and blue. We call them term variables. We defined a behavioral trace type system, and in addition to data type tau, every program command M is assigned a trace type sigma. Trace types capture probabilistic effects and control flow information. They track control flow via checkpoint expressions, and term variables can appear in checkpoints. Trace types are unordered map from term variables to types. For example, we can construct the trace type for this PCFG function as follows. There are two term variables in the function body, so there are two entities in this map. The first entity records the type of term variable A is the unit interval, and the second entity is a branching type. It records the branching condition as its checkpoint. In the Zhang branch, the nested trace type records the type of C is real, and in the Zhang branch, there are two recursive calls. This two recursive function call makes FPCFG a recursive type definition. Having these checkpoints in trace types allow trace types to express control flow decisions. Trace types can be automatically inferred in a syntax directed way like this. And this is how the type definition of FPCFG looks on paper. This is a guide program for PCFG. These two programs can be assigned the same trace type, so they must agree on control flow decisions. It is guaranteed that this model and this guide program are absolute continuous with respect to each other. In fact, Our Soundness theorem of the type system says that compatibility typed program pairs satisfies AC. Now we have a type system that ensures AC. And we also need a way to analyze dependencies in programs. In Fidelio, we use PDGs, program dependence graphs, to modularly capture control dependencies that cannot otherwise be expressed by Bayesian networks. Data nodes are drawn as rectangles. They are sources of data dependency edges, which are drawn as black solid arrows. Control nodes are drawn as rounded rectangles. They are sources of control dependence edges, which are drawn as gray dashed arrows. There are 3 special nodes per function: the function entry point, the syntactic conditioning sink to which a function's return flows, and the hidden state. The hidden state represents correlations involving function calls. It embodies the historical information correlated with current function's return. We adapt the notion of active trails of Bayesian networks to PDGs as indicator of correlation. There is an active trail between node A and B. This trail cannot be expressed by Bayesian networks, since Bayesian networks do not deal with control dependency. And there's a trail A and node C. There's a control dependence edge with label T from a control node to node C. This means C is in the then branch of this if statement, and entering then branch already conditions on is smaller than 0.5. Therefore, this control node is considered observed, and this trail is considered inactive. So A and C are considered independent. We note that the treatment of conditional independence is syntactic and not proven sound. We leave a semantic account to future work. Based on dependence analysis, we design a guide synthesized judgment as a translation. It takes a time derivation of a model program and also its PDG and outputs a program. This translation is by induction on typing derivations. We formally prove that this translation is type preserving. The synthesized guide program has the same data type and base type as the given model program. And the AC by construction theorem follows directly from the type preserving theorem together with the Soundness theorem. For a well-typed model, this translation is guaranteed to generate a guide program that is mutually absolutely continuous with the model program. Here we have some experimental results on several benchmarks. Here we mention a few. We assess the performance implication of generated faithful yet parsimonious guide. The first benchmark is upside-down tree, which we saw before. In each benchmark, we use 2 baselines, the mean field guide and the LSTM guide. The mean field guide treats all random variables as independent. The LSTM guide treats all random variables as correlated. And in this benchmark, in addition to mean field and LSTM, we also compare 2 Fidelio guides that either return or invert the model's order of sampling variables. If the guide generator is not intelligent about the order in which random variables are sampled, then we may end up with a guide that is almost as dense as the fully connected LSTM guide. This plot shows the training loss, the lower the better, as the training progresses. The sparse Fidelio guide converges to the best solution. We also compute the effective sample size, ESS. A higher ESS likely indicates better sample quality. This table shows the sparse Fidelio guide, which samples random variables in a different order, result in significantly higher ESS than all other guides. The combination of faithfulness and parsimony is a win. In benchmark capture, the model uses recursion. It generates a capture image by sampling probabilistic regular grammar, and the inference problem is to recognize capture tags given an image. LSTM guide and Fidelio guide did almost equally well in terms of convergence and recognition rates. A possible explanation is given by the structure of the model. Because the capture samples from a regular language, the data flow exhibits a linear recursive pattern, and as a result, the model has almost no extra conditional independence for Fidelio to exploit. And unfolded data flow graph for Fidelio guide is almost identical to that induced by an RNN.
Jianlin, I'm going to jump in and give you a 2-minute warning here. Sorry about that. Thanks.
Thanks. We design a second capture benchmark, mask capture. Unlike capture, mask capture samples simple arithmetic expressions from a context-free language, as shown from the data flow figure. By carefully treating the hidden state through the recursion, the Fidelio guide preserves the tree recursive pattern. We expect Fidelio to improve convergence and the recognition rate over LSTM guide, and experiment results confirm our belief. Fidelio outperforms mean field and LSTM guide by a large margin. The LSTM guide did not start to pick up until the network capacity was raised to 2 million. In contrast, with limited network capacity, Fidelio can do better. Conditional independences inherent in PCFG-like models make them favorite application for Fidelio. And at the end of this talk, this table evaluates the expressiveness of Fidelio's type system. Previous work either does not support for generality of control flow or does not allow guides to sample random variables in a different order than model. To conclude, we have introduced a method to automatically synthesize scatter programs for deep amortized inference. It uses a type system as an argument for soundness, and it uses symbolic dependent structures to aid in neural network-based inference. And thank you for your attention.